Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Antenna Matching, small overview of the service and portfolio. Our speaker is Jose Matos. He will hold the presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the webinar control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. Also, the recording will be available at our website shortly. But now, I will hand over to our speaker, Jose, and I wish you an exciting presentation.
So, hello everybody. Welcome to the webinar of Antenna Matching, small overview of the service and portfolio of RF. My name is Jose Martos and I am the product manager of RF components of Würth Elektronik. So this webinar is divided in three different parts. So first we will have a short introduction about the time we are living right now, the IoT era. Then how important are the antennas, are becoming the antennas in this time. And we will talk about the advantages of the chip antennas. Then we will go to the impedance matching, so why we need a matching for the antenna and why is that important. We will see few parameters that are very important to see if our matching is right or not. And we will also describe the Smith chart tool. This is the tool that we use actually for the antenna matching. And in the end, we will talk a bit about our service, antenna matching service, and about RF portfolio. So as all of you know, we are right now in the Internet of Things era, the IoT. That means all devices, all kind of devices from industrial automation, healthcare, home automation, smart cities, everything is connected to a network. And in most of these cases, the connection to the network is wireless. That means the antennas are playing a very important role nowadays. And there is one more thing. So everything tends also to get smaller and smaller. So the devices are trying to get always miniaturization. So that means the antennas has a big challenge here because the bigger the antenna is, then the easier it is to achieve a good efficiency. But for small space, the antennas have a big challenge in order to get a good performance. So for these kind of applications where we need the miniaturization and good performance, we have three different types, or normally there are three different types of antennas. We have the wire antennas, PCB antennas, and chip antennas. The wire antennas are low cost solution. They are easy to design, and they are a good solution if space is not that important. But in general nowadays, that is a big issue, the space. So we all remember the mobile phones 20 years ago, they had all the big external antenna, but this is nowadays impossible to see, impossible to imagine. In case the space is important, then we have the PCB antennas or chip antennas. PCB antennas, they offer a high performance and they don't require always the matching. However, they need a RF expertise because not everybody can design a PCB antenna. You should know, you should have this know-how design a PCB antenna. And also it's not that very flexible, because once you have your prototype with your PCB antenna, if it doesn't work as you expected, if the antenna is not emitting in the frequency range you wanted, or with the performance you wanted, then you have to redo this prototype, this whole PCB. And on the other hand, we have the chip antennas. The chip antennas are very small size. They are easy to integrate. They are more flexible, because if one antenna is not emitting in the way you want, you can always change it, and it's not that difficult. And you don't require this know-how how to design anything, because you just buy it. The only disadvantage of the chip antennas is actually that they need the matching. So we will go in detail to explain what is this matching and how we can solve this issue. So the chip antennas, they have a multi-layer chip structure. That means there are layers of ceramic, and in the middle, so with electrodes, there is a coil, or, well, depending the type of antenna. Then they have high permittivity ceramic mix, and they emit in an omnidirectional direction. And as I commented, they are easy to integrate. So we do have chip antennas in our portfolio. The series is called WE-MCA, and there we have two different technologies, all of them with ceramic, but one is LTCC antennas, and the other one is multi-layer antennas. So the difference is just in the production. So the LTCC is low temperature confined ceramics, but anyway, both of them are done with ceramic material, and both are very low profile, and they need small space. Multi-layer antennas, they require a bit less, smaller ground clearance, and the ground must be also connected to the antenna. This is the main difference, actually. But both of them, both technologies, the whole MCA series, we offer many different antennas for the typical frequency ranges, for GSM, GNSS, smart home, Bluetooth, Wi-Fi, and so on. And now let's go to the main topic here, so the matching. So as I commented, the chip antennas, they most of the cases, they require the matching, the impedance matching. And what is this? So in case you don't know, in every transition in the system, in a circuit, there may be a difference in the impedance. If there is no difference in impedance, that means I will do the laser point here. So we have here our transmission line. This has an impedance, ZO, and we have our load. In our case, in most of cases, is the antenna. If these two impedances are the same, then there is no issue, there is no problem, because the ratio between voltage and current stays the same, so it keeps the same, no problem. So the incident wave is going to be forwarded 100%, no problem here. We can imagine this as a, yeah, the transmission line is a pipe, a water pipe, and the load is another water pipe. And the diameters of these pipes are going to be the impedance of the load and of the transmission line. So if both diameters are the same and we make the pipes together, then the whole water is flowing, no problem. We don't lose any water here. But what happens if one of the pipes has a bigger diameter than the other one? Then if we make them together, at some point we will lose water. Some water will be dropped off. The same happen in the circuit. So if we have a transition and the impedance of the load is different than the impedance of the transmission line, then we don't have a stable voltage divided by current. And this voltage and this current, it cannot be removed, or it cannot be created. So it will be reflected. So we don't lose the signal, let's say, with heat. We will lose the signal by reflections. So the incident wave is not going to be forwarded wave. That means the wave that we send to the load is not going to arrive 100%. That, I mean, these reflections means at some point means losses. No, we are losing some signal here. So what do we need? Coming back to our pipes example, we need a transition pipe section. That means we need a section where one part is going to be the diameter of the first pipe, and the other part of the transition pipe section is going to be the diameter of the second pipe. In this way, we will not lose that much water. And exactly the same is doing this impedance matching circuit. So if we have here the transmission line impedance, or the source impedance, we should see here an input impedance of matching circuit and the load, that should be the same as the transmission line impedance. And the same here, the output impedance here should be same as load. No? So this will minimize the signal reflection and will maximize the power transfer to the load. So it's of course good. And how do we know if our matching is right or not, if it is well done or not? So there are many parameters to describe it, to see. All of them are connected actually. So first is the reflection coefficient. So the reflection coefficient is the ratio between the reflected voltage and the incident voltage. We can calculate it with the load impedance and transmission line impedance. And yeah, we can see really easily if both impedances are the same, we said that there is no issue, no reflections, that will be zero, no? So the reflection coefficient is zero. No reflection, this is the ideal case. If this is -1 is short circuit, if it is +1 is open circuit. So this reflection coefficient will be always between -1 and 1. And we normally used to talk about the module of reflection coefficient if this is going to be between 0 and 1. So if it is 1, everything reflected. If it is 0, nothing reflection, no reflections. Then we have the return losses. This is kind of a way of showing the reflection coefficient, but in dBs. So we see here the formula, or we can describe it as the ratio between reflected power and incident power in dBs. So if this is 0, means return losses is 0, means that everything is going to be reflected. If it is very high, so infinite, in the ideal case, is going to, we will have no reflection. It's going to be perfect match. And then we have the voltage standing wave ratio, VSVR. We will see in the next slide what is this, but we can, from the formula, we can just easily see that if the module of the reflection coefficient is 0, that means perfect case, no reflection, VSVR is going to be 1. So this is the ideal case. Then if this is increasing, this VSVR, that means we will get worse and worse. I mean, the system will get worse and worse and more reflections. If it is infinite, everything is reflected. If we are between values of 1 and 2, then our system is well matched. I mean, more than 90% of the power is going to be transmitted. So this is good, of course. And what is this voltage standing wave ratio? Well, if we have a transition, we said that some part of the incident wave will be reflected. So the incident wave and the reflected wave, at some points, the phases will be adding each other. At some points, they will cancel each other out. That means that we will have in this part of the transition, we will have a standing wave, and this standing wave is changing. No, so it has a maximum value and minimum value. So the ratio between the maximum and the minimum is this VSVR, this voltage standing wave ratio. So from here we can see that if this is 1, that means maximum and minimum is the same. So there is no variation here. That will mean that there is nothing reflected. So there's just we see just the incident wave. We don't see any reflected wave there. Let's see a couple of examples just to understand these parameters that we just saw. So we have our transmission line. This is let's say, a schematic of our evaluation board of the antenna. So we have a transmission line. This is always 50 ohms, and our antenna. If our antenna has here 60 ohms, then the difference of impedance is not that high. So we will get a reflection coefficient of 0.1, which is close to 0. It's good. And VSVR is 1.2, so close to 1, close to the ideal case. In this case, our antenna has a good performance. It will emit with no problems. But what happens if our antenna has 150 ohms? In that case, then the reflection coefficient is already 0.5, so the half of the signal is going to be reflected. And VSVR is going to be 3. We will see in a moment in a table, is not that bad, but yeah, it's not anymore that efficient as before. So our antenna, it will emit in this case, but not with that good performance. So as we could see from the formulas, all these parameters are related to each other, no? And here we have all some cases just to see what is the perfect match and what is still good and what is not. So a perfect match is reflection coefficient 0, VSVR 1, 100% of power will be transmitted. I already said that if VSVR is between 1 and 2, then we have a good matching. That means yeah, at least 90% of the power will be transmitted. This is good. But if we have, for example, the VSVR 3, as in the just previous slide, that means that 75% of the power will be transmitted. It's not that good anymore. And of course, the higher this number is going, this VSVR, the less power we will be transmitting. And the total reflection is, yeah, reflection coefficient already 1, and return loss is 0, and transmitted power 0. Then you may ask, if you already know our series and you have seen our datasheet, you could think, okay, this is good to know, but why do we need to know how to do the matching if in the datasheets we are specifying a matching filter? This is true, we specify a matching filter in our datasheets, but this is very important. This matching filter that we specify is only valid for our antenna on the corresponding evaluation board. That means, yeah, if you want to test our antenna, you just purchase the antenna and the evaluation board, the corresponding one, and then you can use this filter that we recommend, and the efficiency of the antenna, the performance will be good, and you can test it, and it will be great. However, if you take the same chip antenna, this chip antenna, and you place it on your product on a different PCB with different thickness, with different material, with different components around, with a case of the product, the antenna will change a lot, the performance, because everything has an influence on the antenna. That means this this matching filter is not valid anymore. So the one that we recommend is not valid for different product, different PCB. So you should do a new matching for the product. And this matching must be always in the final product with the case as well. Because if you only match your PCB, maybe the matching is great, but then when you add the case, the final case, you have the final product, then the antenna may not emit in the same way, so that with the same performance. So that's why we are here. So to explain what is the process to match your antenna. For this, we use the Smith chart. So I don't know if you are familiar with it. We will go in detail. So the Smith chart is a graphical calculator used for solving complex numbers, complex problems of transmission lines or matching circuits. And is great because we see, first of all, it's graphical, it's not many numbers. This is always more comfortable to deal with. And the second point is that you have many RF parameters in one representation. You have many parameters at once. So the red lines, for example, here that you see, those is impedances. So the blue lines are admittances. The green circle is the VSVR, and you will have many of them if you use the tool. Then you have as well the reflection coefficient, as we will see in a moment, etc. And just the most important part here, if we are in the center of the Smith chart, right center, that means we have perfect case, so the ideal match, nothing will be reflected. Okay, and this is always our target when we work with the Smith chart. So let's explain a bit more about what means everything in the Smith chart. So we have impedance. The impedance in high frequency has two parts. So the real part is the resistive part, and the imaginary part is the reactance part. No? So the circles here are showing the resistive part. The circle which is crossing the center of the Smith chart, this is the circles of 50 ohms, or if we normalize, because we will normally divide by 50 all these values, so we have 1. Then the closer we are to the right, that means the closer, the higher will be this resistance. And the more far away we are, then the smaller will be this resistive part. And then about the blue lines, those are the reactants. So the closer these reactance lines are to the x-axis, then the smaller will be the value. Okay. So now we have an example just to see how to find our point in the Smith chart. We have our transmission line of 50 ohms as always, and we have an ideal inductor and ideal resistor. The inductor is 100 ohms of reactance. The resistor is 25 ohms of resistance. Okay, those are both ideal. So if we normalize this, then this should be the 2 and this is 0.5. So the resistor first, we will be, and if we see the resistor first, we will be here in this circle, so at some point of this circle, because this is the circle of resistive part 0.5, okay? And if we check this, the reactance, we should be in the line of reactance 2, which is this one. So the intersection between these two lines, so between the circle and this line, this is the point where we are right now. Actually, also, as I commented before, we have many parameters, no, at once. So we can also see the reflection coefficient here. If we measure the distance from the center of the circle, or the center of the Smith chart, to this point, we will get the module of the reflection coefficient. And if we measure the angle between this vector and the x-axis, we get the phase of the reflection coefficient. So this is one more example of one more RF parameter that we can see only with the Smith chart. So this is what I just commented. If we are in the center, then reflection coefficient is 0. So perfect case. If we are at the border of the circle of the Smith chart, it will be 1. So everything is reflected. Then what happens if we add a capacitor? Again, ideal capacitor. So this ideal capacitor will have 75 reactance, minus 75. That normalized will be minus 1.5. Since the resistive part didn't change, because again, they are ideal, so we have still 25, we should be at some point still in this circle. And the movement will be just going down, so from the line of 2, reactance 2, to the line of reactance 0.5, so until this point. And we can see, just adding this capacitor, the movement down is getting closer to the center, so we have a lower reflection coefficient and different phase as well. The same that we had with the admittances from the right, we have the the impedances from the right, we have the admittances from the left. So the circles are showing the conductance, and the blue lines are showing the subsistence. And then if we get closer to the left, it is the short circuit. I forgot to say before, if with impedances we get closer to the right, we have the open circuit. And then if we cross just the circle which is crossing here, the center of the Smith chart, this is the conductance 1, and the closer, higher conductance, far away, lower conductance. Is the same system. And the same happened with the substance. So the closer we get to x-axis, the smaller will be the value. So from these examples and from all this data, we can get how we will move depending if we place an inductor or a capacitor in series or in parallel. So always that we work in series with components in series, we will move with the impedances circles. If we place the components in parallel, we will move with the admittances circles or lines. Okay. If it is an inductor, we will move always in the upwards direction, because the upper half of the Smith chart is the inductive half, and the below part is the capacitive part. So when we place a capacitor, we will move always down. Okay. We will, the resistors, they are moving in a different way, but this is not important for us right now, because for the Smith chart, for the matching, we will never use resistors, or almost never, because the resistors are just making the signal to be lost. So resistors means losses, and this is what we want to avoid for the matching. So let's see one example of how do we do the matching in our lab. Here we have our antenna, and with the corresponding evaluation board. The transmission line of this evaluation board is 50 ohms always. And first we do a short. We do a short and we measure the impedance here for a certain frequency. This is important. The impedance is different for depending the frequency where we are. So it's not the same to match the antenna if we want 2.5 gigahertz, or we want 900 megahertz. So in this case, we measure an impedance of the load of the antenna for 2.45 gigahertz, which is the typical value for Bluetooth or Wi-Fi applications. And we get this value, 25 and 100 J. Okay, so it's easy to see that here we have different impedances from the transmission line and the load. And if we do the calculations of the parameters that we have seen before, you see that the module of the reflection coefficient is 0.825. That is very close to 1, so very close to the really bad case, so total reflection. So this system is not going to be so good transfer, as we can see here. So the transmitted power is going to be 32%, and the VSVR is higher than 10. This is really bad. So in this case, we need for sure a matching. So as in most of the cases, actually, we need a matching. And what is the aim? We already saw. So the aim is that the input impedance of this matching circuit plus the load is going to be same as our transmission line. So it's going to be 50 in the end. So first we will see where we are. No, we have 25 and 100 ohms. We should normalize, but in this case, this Smith chart is showing the values denormalized. So we have here the circle of 25 is here. So resistive part in our case is 25. So we should be somewhere here, and 100 J. So this is this reactance of 100 is here. So the intersection is here. Is same as before. And then the possibilities are huge. So we have many different possibilities. We could move until here, and then with a capacitor in series until here, and then capacitor in parallel here, or capacitor in series until here, and then we will have an inductor in parallel, or we could go also to the other direction. There are many possibilities. In this case, we chose this option. So we have a capacitor in series of 0.52 picofarads. To get this value, there are many tools in internet. So you can find many Smith chart tools where you will get this value easily without any calculation. Otherwise, you need to do many calculations. And with this capacitor in series, we will achieve this movement down, because we go to the capacitive part, this is a capacitor, and we finish in this point. So in this point, new point, we have 0.5 minus 0.5 normalized value. If we calculate, now the reflection coefficient is already 0.44 and 7, and the VSVR is 2.61. So we improved the efficiency of our system a lot, from 32% to 80% of transmitted power, only adding one capacitor. So yeah, it looks already good, but still, the VSVR is higher than 2. We can still improve it. So aim now is going to be to add something to be in the middle. In this case, of course, I'm also talking about a system, a filter only with two parts. Normally, you use a P filter or T filter, so you have more movements even to do, because you have three components or even more. But we want to simplify it, so we are using only two components. So now we want to go to the center. We want to go higher direction, so north, let's say. So you need an inductor. And you want to move with the blue line. The blue line is the admittance. So you want an inductor in parallel. So this is what we use here. We have our inductor of 3.3 nanohenries in this case. And with this value, we will achieve this movement to the center. And in this point, so if we are really in the center, we manage to have a reflection coefficient of 0 and VSVR of 1, and transmitted power is 100%. Of course, this is ideal case. We are here always talking about ideal cases. In the reality, is never that easy, and it's never, yeah, the reality, the practice is never following the theory that good. First of all, because these capacitors and inductors, they have many parasitic effects. So the movements are never that perfect. So the capacitor has also inductive parasitic effects. They have also some losses. The same happens with the inductance. So this movement is never that perfect. Is maybe like this, or going to other direction. No, is never that good. Also, these components, they have tolerances. No, this inductor is 3.3 nanohenry. This is available in our portfolio, so it's a real value, let's say. But normally it will have a tolerance, and it will have a tolerance of maybe 0 plus minus 0.2 nanohenry. And this 0.2 means that maybe we have here 3.45 or 3. I don't know, 2. And then this change, this variation will change a lot here. although maybe you think, oh, this is not a big deal, it changes a lot in the Smith chart. Actually, here we have an example. No, we have the antenna, the efficiency of the antenna, only placing a capacitor, then capacitor with the inductor. But between these three, only the value of the inductor is changing, and not much. So, for example, between the red and the blue one, the only difference is 0.6 nanohenries. So you can see that only 0.6 nanohenry is changing a lot the efficiency of the antenna. So that's why, yeah, the matching is never that easy as it looks in the practice. So of all these things we have seen, we get the conclusions that first of all, the matching is very, very important. So we also show in our datasheet sometimes the difference of the antenna without and with the matching. So without the matching here, we see that the antenna is going to emit for sure. I don't say that the antenna is not going to emit anything, but the performance can be improved a lot with a matching. So from minus 15 dB to minus 35 dB. So yeah, we can see that with the right matching, the performance of the antenna is going to be increasing exponentially. Then also, a very important thing that I already commented is that the matching is going to be different for every different product, every different PCB. So you cannot use the matching that we recommend in our portfolio. You should do a new one for your product. And then the point that I just commented is that the huge difference between the theory and the practice, because in the theory you always deal with ideal components. In the practice, they are never ideal. So you have many variations, and you have to play a lot with the components in the reality, in the practice. All these points together give us the conclusion that this matching process, it requires some RF expertise and of course also RF equipment. So in case you don't have this RF expertise, or maybe you have it, but you don't have the equipment, or maybe you have both, but you have some questions, you have some problems, you should know that we offer full support to our customers with the matching process. So in case you have any question, any project, whatever, just you can go to the sales contact of Würth Elektronik and explain him, and then he will contact us for the project, and we will let you know how to go further, how to accomplish the matching. We have also an email address for any question. This is antenna.matching, the online DE. And moreover, if you want to know something more, you want to have more information regarding antenna placement and matching, you have available in our website the app note of WE-MCA, multilayer chip antenna placement and matching, because actually this presentation is oriented to the matching, but also the placement of the antenna is important. Also the space, the ground clearance that you have to design for the antenna is also important. And this topic, I didn't say anything about this in this presentation, but it's very important, and it will be described in this app note. And the last thing is that, of course, once we have a project and we recommend or we suggest a filter, these inductors and capacitors of the filter will be with our inductors and our capacitors, because we have a wide portfolio of RF. So we do not have only LTCC, which we also have a good portfolio. So we have antennas as commented, but we have also cheap low pass filters, band pass filters, balloons, and common mode filters for high speed rates. But we have also the RF inductors with all different technologies available in the market. So we have a wide ceramic inductors, which offer very good performance for a good price. We have wide ferrite inductors for higher inductance values. We have multi-layer ceramic inductors, very, very common because of the low price, and they are robust. Then the thin film inductors with a very, very low profile and good precision, they also offer good performance. And then we have the air coils with no cores or no losses, the highest quality factor available in the market, and the flat wire air coils for very high current applications. But yeah, in the filter, as we saw, we have inductors, we have also RF capacitors, and we also offer them in our portfolio. This is the VCAP CS RF. And if we are talking about RF, at some point you will also need some crystals or oscillators. We do have also them available in our portfolio, and coaxial connectors. Or if you just need at some point a final solution, a complete solution, we have also wireless modules in our portfolio. So this is all from my side. Thank you very much for listening. I hope you found it interesting, and I hope you learned something. Yeah, and if you have any question, now is the moment. Or if you have in the future any question regarding the matching, feel free to contact us. Thank you very much.
Yes, thank you, Jose, for your interesting presentation. As you already mentioned, now we would like to turn our attention to your questions, and you can enter them in the chat function in your webinar control panel. So, Jose, let's take a look at the questions within the chat. Maybe a first question. How solder mask on PCB influences impedance or construction of Smith chart? Is it better use solder mask or have just bare PCB?
Excuse me. How's the most PCB? Well, you need to solder, and if it is with a solder mask, the result will be better because it is more constant. However, when you do it in the lab, so when we do the matching in our lab, we have to do it manually. Otherwise, yeah, it is difficult to or difficult, not this longer process. So we do it manually, and it doesn't change that much. But in the end, it's better with a solder mask because it will be more constant and it will be always more similar. No, so yeah, it is changing a bit. If you do it manually, it's not that perfect, but in the end, for the process, is much more comfortable or faster to do it with manually.
Okay, thanks.
Mhm.
Another question is what would be the difference if we are replacing RF inductors with ferrite inductors?
A big one actually. Well, any kind of different technology will change a lot because different technologies, they have also different parasitic effects. So for example, if you are using a ceramic inductor, and actually also between ceramic inductors, the different technologies. So if you have multi-layer ceramic inductors, those have less capacitive effect as wire wound ceramic inductors. Um, so then the movement in the Smith chart will be different also. The same happens with ferrite. So the ferrite, it has more losses, for example. So the resistive part of the ferrite inductor is going to be higher than a ceramic inductor. So also the movement will be different. So yeah, it changes a lot. We used to do our matching, unless the customer requires other thing, we used to do it with multi-layer ceramic inductors because of they are comfortable to solder as commented. So we do it manually, and the wire bond inductors are not that comfortable manually. And second thing, they are low cost. They offer good performance for low price, and yeah, and they are ceramic, so they have less parasitic effects as yeah, wire wound or ferrite inductors.
Okay, thanks. And maybe one last question. Does parallel G&D area for GPS sensor in PCB make sense? Does it make sense to connect the parallel G&D surface with level wires?
Does it make sense to sorry, that's parallel GMD. Well, actually, this I don't really parallel different BS. This I'm not really sure. Actually, I'm sorry, I cannot answer. So we will check it out, and I will give you an answer per email. For sure, it is interesting question, but I have no experience with this actually.
Okay, perfect. So we will answer this question afterwards.
Mhm.
And if there are any other questions left, we will answer them via email. But for now, we are finished with this presentation. Thank you very much for your attention, and I hope you enjoyed the presentation. The next presentation topic will be successful design of SMT spacers by choosing the right option, and the presentation will start at 9 a.m. So see you there and enjoy our digital days. Goodbye.
Thank you. Bye.